Uh, okay, so let's start now. Uh, so we will. So my name is Sathasivam, and I am from ICTVM, and this is the week 2 of the tutorial. So what we are going to do this week is basically we will just browse through the limit once again, solve a few problems, and then we will move on to continuous functions, and then the maximum value theorem. So yeah, I forgot to mention we will also do the intermediate value theorem also. And finally, we just to do a few problems in supremum and infimum. Okay. So mostly what we are going to focus on is limit, continuity, intermediate value theorem, and supremum. This we will do little bit, maybe not much. Okay. Because I will explain why I just want to do little bit, but not much. Okay. So let's proceed to the problems directly. Should I keep this view or this one? Which is better? I think this would be better, right? So we'll keep this view. So let's proceed. So the first problem is we want to find the limit of this particular function here. So it's a polynomial function and you have to apply the limit to it. So that's a question. So if you want to find what you know is if you have two function f and g. So if you look at the limit of f plus g as x tends to a, this is nothing but the limit of x tends to a f plus limit of x tends to a g. So you can split the limit like this, and you apply the limit on both of these separately, right? So let's what we are going to do is we are just going to apply it like this here. So the limit of x tends to 2. So 8 minus 3x plus 12x square. So this will be limit of x tends to 8. So minus limit of x tends to 2, 3x plus limit of x tends to 2 on 12x square. Okay. So now you can directly apply the limit on each of this. And what you get is this is a constant. The first one is a constant. So applying limit does not change it. The second one, this is 3x. And you know, this is a constant. So you can apply the limit on each of this. So the limit is nothing but you just substitute the 2 here. Because of this function is continuous. So the limit value is nothing but f of x. So I can write here. So this is 3 times 2 plus 12 times 2 square. So if you compute, you will get a 2 plus some 48, which is 50. So you have some algebraic operation you can do with the limit. So first one is the addition you can do. If you have addition of two functions, then you can apply the limit directly. So there are few more, I mean, which we have already done in the class. And if you have multiplication also, you can do. But division, you have to make sure, you know, the denominator is non-zero. Then you can apply the limit. Okay. Okay, so let's move on to second question. So first one is actually quite easy. So it starts with the easy questions, and as we proceed, we will see some more interesting ones. So this is the second one. You can answer it if you want. So okay. So you said it's 3. Okay, let's see. So you're going at the limit x equal to 1 and this one, right? So here what happens is here you have a function which is uh, basically if you draw here, there are basically two different lines are there. From here it is like a parabola. So something like this, let's say. But in this side it's a straight line. I mean, I don't know how the straight line, which direction it looks like. One has to see it. But it's basically two different function. At the point 1, they are kind of the same. So when you have a function like that, what you have to find is basically you have to find both the right hand limit as well as the left hand limit. So let's find the right hand limit. Limit x tends to 1 minus f of x. This is nothing but limit x tends to 1 minus 7 minus 4x. And then we apply the same thing. The limit of sum is basically sum of the limit. You apply it here. And then you will get 7 minus 4, which is a 3. So in this direction we got 3, and then we'll check for the right hand limit also. So let's look at the limit x tends to 1 plus f of x. Okay. So this is limit x tends to 1 plus x square plus 12, right? X square plus 12. So this is 1 square plus no, x square, not 12, x square plus 2. Yeah. So 1 square plus 2. So this is also 3. So we checked both the right hand limit. So you have a 1 here, and you are coming in this direction to 1 as well as this direction. Both direction you got the same limit. Okay. So that means your limit is basically your limit exists and it is actually 3. So limit x tends to 1, f of x is 3. So far we haven't done anything significant. These are just trivial examples. So let's probably do something little interesting. So in this problem, what you're going to do is you want to find the values of y for which this function f of y is continuous. Okay, so here I have y, and I want to find, okay, for what are the values such that this f of y is continuous. So you can take a minute and probably try to solve it. So you're so quick. Okay, so you're claiming it's minus 4 and 1, right? Okay. So you want to explain why it is the answer? You can explain if you want. So denominator became 0 at this point. Yeah. Okay, that's correct. So at this point, this function is not continuous, otherwise it's continuous. So I will just explain it a little bit because for the other people. So you have a function which is basically of the form, your f is basically of the form let's say some g of x by h of x, right? So both of these are functions, and your f is basically quotient of these two functions. So what we know is if you have something like this, and if both f and h are continuous, then we know is the f is continuous. Okay, so if you look here, both of these functions are continuous. Okay, but provided if h of x is not equal to 0, then this f is continuous because it's a quotient of two functions. So the f of x is not continuous only when these points are 0. Okay. So because these two are continuous functions, a quotient of a continuous function is continuous as long as the denominator is not equal to 0. Okay. And those points where the denominator is not equal to 0, the quotient is continuous. So that means if you want to look at not continuous, that means basically you are going to find the points which uh, find all the points on which this polynomial has a root, right? So basically what you have to find is you have to find the points such that, so you can see here. So the polynomial in the denominator, which is 3y plus minus 4. So this has to have a root. Okay, so find the root, you just apply the formula, which is a minus b plus or minus square root of b square minus 4ac by 2a. So you just apply the formula. You will get minus 3 plus or minus. So this is 9 minus, this is minus 4 and 1. So which is plus 16, I think, by 2. Okay. So this is minus 3 plus or minus 5 by 2. So which if you compute it, it is either 2 by 2 or minus 8 by 2. Okay. So in this case, you will get the answer is 1 comma minus 4. Okay, I'll start the recording again. We'll start. Okay, so you have a comment. So let me just read the comment here. Oh, okay, the comment is gone, but I mean it's gone in this, but anyway. So yeah, as you said, it you can only talk about the function where it is defined. Of course, that is correct. So basically, the function is not defined on those points. Uh, and yeah, and that is correct. So other than those points where the function is not defined, it is actually continuous. So yeah, but what I was telling the using this is basically if you have two functions, uh, and basically if you take the quotient, so the theorem says that this function is defined provided the h of x is not equal to 0, and wherever it is defined, this is continuous also. So wherever it is defined, of course, it's continuous. So yeah, what you said is correct, because on those points where you have minus 4 and 1, the function is not even defined. So continuity does not make sense. Yeah, that's correct. But other than those points, see, one thing is to prove. Say, what I'm asking is the function is not continuous. What are the values of y at which the function is not continuous, right? That means I have to say, okay, minus 4 and 1, the function is not defined. That is fine. And those points, it cannot be continuous. But then one has to also have to say the other points, it is continuous, right? So that these are the only points that the function is discontinuous, right? So the other places, how do you prove it is continuous? It's basically you have to use the theorem where if you have a function f of x is g of x by h of x, and if h of x is not equal to 0, if you are both f and g are continuous, so is h. Okay. So is h is continuous exactly on the points where this h of x is not equal to 0. Okay, so let's move on to next question here. So the next question is you have a you have a function here f, which is a real function from R to R, such that the limit of f as x tends to a exists. Okay, so basically what you have is the limit exists. Now the question is, does that means the function is continuous? So there is an answer. It says yeah, it's false. And can you give me example? Or maybe I'll give you example, and then we will. I will have some more questions to be asked. So let's try here. Mm. So there is another comment. I will check that also. So 1 for all x, not 0. Yeah. So some such functions one can construct. Okay, I will just go with whatever the function that Advait is telling. Okay, so one can construct so many functions like that. So, but let's construct one of this. See, basically, what the problem tells is that you have a function such that the limit exists. So, basically, what it tells you is as you get closer and closer, let probably just try a function. Okay, let's say a function is like this. It's a constant everywhere. Let's say except at the point 0, it is not constant. It is, let's say, it's became 0. Okay. So f of 0 is 0 and f of x is 1 if x not equal to 0. Okay. So there's another comment, I think. That means as long as denominator is equal, then it will be continuous. Yeah, so in this problem that is true, because you have this theorem uh, which says that if you have a quotient of two functions such that if both of them are continuous, uh, then what happens is whenever the denominator is equal to 0, the quotient does not make sense, right? So we don't able to define a function when the denominator is 0. So we ignore those points where the denominator is not equal to 0, and all those points the function f is continuous. Oh, sorry, I have written it wrongly here. So, if g and h are continuous, so is f are continuous at x, then so is f. Yeah, so you are right. As long as the denominator does not equal to 0, no, not only the denominator is not equal to 0, you also need these two functions have to be continuous. So if you take a quotient of a continuous function, it is continuous as long as the denominator is not equal to 0, because those points you cannot define the function, define the quotient. So wherever you can define the quotient, it is continuous, provided if both of these are continuous. So basically what we are finding here is to find the points where the function is not defined. So when it is not defined, I mean, it's not continuous, right? Basically, we are not talking about the function there itself. So, okay, so let's come back to this problem. So I'll just recall what we are doing here. We have functions such that the limit exists, okay? But the question is whether it is always continuous. And the answer was given, I mean, and what we are expecting is that the okay, it's not true. Okay, and the example was given by one of the student. So what he said is you take a constant function here, except at one point you just change it. Okay, now this function is continuous. So this function has a limit, but it is not continuous, right? So basically the existence of limit, what it tells you is as long as you coming closer and closer to this point, closer and closer to 0, what is happening is what the limit captures. It does not capture what exactly happened at that point. What continuity does is it also captures what happens at this point also. Okay. So since the limit, if you look at x tends to 0, f of x, so the limit is 1, but which is not equal to f of 0. Okay. So thus this function is not continuous. So see, there are there are some good theorems along this line. Okay, so this continuity is there, right? This kind of continuity are in some sense little bit special. Okay, why? Because I can just redefine this function, redefine this point, and then I can make the function continuous. Okay, so what I'm trying to say is it is not continuous at 0, but I can change this value so that this function became continuous. Okay, how will you do that? Uh, so you have basically your function is f of x equal to 1 for all x not equal to let's say for all x not equal to 0, and f of 0 is equal to 0, right? So this is your function. But if I just change at the point 0, then I can make this function continuous, right? How? For all x not equal to 0, define the g of x is also 1 at 0 also. Okay. So what I was trying to say is I can just change this particular point, only the function value at this point, and I can make this function continuous. Okay, when I have function like this, so this type of discontinuity are called removable discontinuity. Okay. Why it is removable? Because say I can just by relabeling I can remove the discontinuity. So I have a discontinuity in my function, but then I just change one point. See, I'm not changing anything around the neighborhood. Just changing this one point makes it a continuous. Okay. So in that sense, I can remove the discontinuity, and hence this kind of discontinuity are called removable discontinuity. But if you want things, not every discontinuity are of this form. Okay. So in general, you cannot say anything. So let me draw another example. Uh, I just want to tell you like there are different kind of discontinuities. Okay. So let's say I have a example like this, where I'm coming to -1 here, and I'm going to 1 here. Okay. So at 0, let me just map it to 0 again. Okay. So f of x is equal to -1 if x is less than 0. F of x is equal to 1 if x is greater than 0. And at 0, I just define it to be 0. Now, if you have a discontinuity like this, see, now you cannot, is this a removable discontinuity? Can I just change this one point and make it a continuous function? So you cannot do that, right? So in general, depending on the discontinuity, you can either remove it and make it a continuous function, or you cannot. Because this type of discontinuity, what happens is you are basically jumping from here to here, right? You're going like this and suddenly you just jumped here. So this type of discontinuity are called jump discontinuity. Okay, and there are, one can give few more examples. There are different, many other types of discontinuities one can discuss, but yeah, but we are not going to do much about the types of discontinuities. But there are something known about the type of discontinuity, and if you have monotonely continuous function, okay, so basically if you have a function, uh, so let's say you have f, which is continuous, and as well as increasing or decreasing. Okay, so basically and increasing. Let me type monotone function. Monotone. So what I mean by monotone? So I'm not defining here, but just telling you. So if you have a function like that, that is monotone. But if you have a function like this, that is not monotone. So monotone is basically a function which is, if it increases, it either increases, or if it decreases, it either decreases. I mean, it cannot go up and down. Okay. So such function, or if you want to define, you can say f of x is greater than or equal to f of y whenever x is greater than or equal to y. Okay. So this kind of functions are called monotone increasing, and one can define the monotone decreasing functions. So if you have this both continuous and monotone, then you can kind of know how the discontinuity of the function will be. Okay. Uh, so not continuous and monotone, but yeah, it's just a monotone function. So if you have a monotone function, then the discontinuity is one can describe. Not completely. Not. I mean, of course, one cannot say where exactly the discontinuity comes, etc. But there are some information you can tell about what type of discontinuity this function can have, etc. Okay. In general, you cannot say much. So there is some theory about the types of discontinuity, but of course we are not going to do it. I'm just telling you there are even though the discontinuities are there, they are of different types. Okay. So maybe I'll just draw one more discontinuity, just as giving a different type of examples of discontinuity. So you look at this function. Okay. So my function is basically sine 1 by x. So my domain of the function is basically, if you want to write the domain, this is from 0 to infinity to r. Okay. So f is basically f of x is sine 1 by x when x not equal to 0. And x equal to 0, we will write f of 0 is 0. So let's say this is my another function, okay? So of course I'm not going to prove, I'm going to draw this function. I'm not going to prove why the drawing looks like that. That's kind of, I mean, understand. When you can put it in a graph calculator and you can check, okay? I mean, later one can see how it goes, but it's not very important for us. So if you draw the function, it goes like this. It starts, but then as it goes to 0, the oscillation became larger and larger. Okay, so I don't know how to draw it though. So it starts with the bigger oscillations. Okay, so but as it goes to 0, the oscillation became higher and higher. Okay, so as it goes to 0, it will become, it oscillates very fastly. Okay, but it's a range bound. It moves from 1 to 1. Okay, so it moves from 1 to -1. But this oscillation started like big oscillations, and then as it goes, it goes, the oscillation became fast. Okay, now if you look at this function, this is not a jump discontinuity, right? It's not at this point you are jumping here or there. You are not jumping. But on the other hand, it is not a removal discontinuity also. Because what happens is near 0, if you look, your function is kind of oscillating. Okay, so it's not, the limit here does not exist. So if you look at this function, and if you want to find the limit of this function, so the limit does not exist. Okay, limit of this function at x equal to 0 itself does not exist. Here also it does not exist, but we are having a jump here. Uh, but here also it does not exist, but it was a little bit different. Oh, I will come back and tell you that the reason that I draw these two examples is uh, when we do the intermediate value problem, we will come back to these two examples. Okay. So right now you just see there are different types of discontinuities one can produce. So you can just see this example. Okay. So this is basically a removable discontinuity where I just change it, and this is a different type, and here I have different type. Okay, so let's move on to next problem here. So here you are going to find the limit of this function. So you can try here. So the limit is 2. Yeah, I'm sure he doesn't know the answer beforehand. Okay, but he is very quick though. So he's telling the limit is 2. So let's try to do it here. Yeah, I'm going to solve it slowly. Okay. Probably I will add some hard problem from the next lecture onwards, so that it will take time for you to solve. So, but anyway, right now we will do this. So you want to find the limit at x equal to 0, right? So what we are going to use is we will use some. See, we know that the limit of f plus g we know. Limit of fg we know, right? If you have something like that, then I can always write this as the limit of f plus limit of g. Okay. So here what I'm trying to say is, see, whenever I define the limit is defined using your limit was defined as for all epsilon greater than 0. So we will write here. If you have a limit x tends to a, let's say if f of x equal to some L. Okay. So the definition, if you want to look, it is some definition will be there. It's for all epsilon greater than 0, there exists delta greater than 0, such that whenever x minus a less than delta, you have f of x minus L. less than epsilon. Okay, so this is the definition. So, but if for all epsilon, if you can find a delta such that whenever this happens. So this is a basically an implication statement, right? Basically, if you look, it is if this, then this. So you have to prove this statement is true. Then you are claiming the limit exists. So okay, that is the idea. But whenever you do the problem, most of the time what happens is you will not go back to this. Okay, so you might have some limit, uh, some limit of some functions are already known. For example, if you look at the limit of x tends to a, let's say x, this is basically a. Okay, so this kind of some limit, and basically what we are going to do is, and then we are going to just use the algebra of limits. So if you have limit of uh, f plus g or fg or f by g, so these kind of limits one can calculate, right? So we are going to use this plus the standard limit we know to solve these problems. Okay, so you have I mean one person has said it's a two, right? I mean it's very easy to say when you do the algebra, I mean algebra of limit, using the algebra of limit. Now I will ask you the question. Okay, can you prove this using this definition? Okay, now it's not always easy. So but the thing is you have to go to this, but most of the time we will not do it. Okay, that's why the idea of doing all these theorems, which helps you, to uh, simplify your life. Okay, anyway, let's try to solve this problem here. So if you look at this, you see there is a quotient here and there is an addition here. So let's split it and then we'll try to solve. So this is limit x tends to 0. I will just zoom out so I can see it. So maybe I'll draw in a different color. So this is limit x goes to 0, x by sin x cos x plus x cos x by sin x cos x. Okay, so I can split the limit like this, and then what happens here is, if you look at this, so if you directly apply, this is a 0 by 0 form, right? So x is going to 0 and the sin x is also 0, cos x is 1 here, and this is also, I mean here I can cancel the cos x. So this will be x by sin x. Okay, so here also you have x by sin x, but what we know is we know sin x by x, right? So what we know is limit of sin x by x as x goes to 0. This we know, this is just 0. Sir, not 0. This is 1. Okay. So now, but we have to work with x by sin x. What we do is we just flip it over. That's all. Okay. So what we do is we look at limit x tends to 0. So we go 1 by sin x cos x by x. Okay. So this is nothing but x by sin x by cos x. Okay, I'm just going like this. Plus, we will do the same thing here. 1 by sin x by x. Okay. So here now we apply the limit. So the limit of quotient is nothing but the quotient of limit. So this will be limit of x tends to 0, 1 divided by limit of x tends to 0 sin x cos x by x, plus you have a limit of x tends to 0, 1 divided by limit of, so x tends to 0 sin x by x. Okay. So if you look, this part is very easy to compute. So limit of x tends to 0, 1. So 1 is a constant. So this is nothing but, so this is 1. The numerator is 1. The denominator is also limit x tends to 0 sin x by x. Sin x, that is also 1. So you have 1 here. So if you look here, this is also 1. But here you split it like this. Okay, so see it as a product of limit. And this part limit we know, this is 1. And limit extends to 0 cos x. Cos x is a continuous function. So that is basically cos 0, which is 1. Okay. So you have here it is 1 times 1. Okay, which is basically 1 plus 1. And that is 2. Okay. So what we are actually doing is we try to use this algebra of limit. More or less that is what we will do most of the times. Okay. Sometimes, but so okay. But suppose if you want to prove, let's say limit extends to 0 sin x by x equal to 1. Okay. If you want to prove this, then algebra of limit is not enough. But then you have to do a little bit more. Okay. So whatever for the purpose that we are doing, this is more or less enough. Okay, probably that is the most that we do with the limits. But before I close the limit part, and probably there will be some more limit comes, but probably I will introduce a small thing. So this might be useful. I didn't prepare. Okay, I didn't prepare much example for this, but there's a theorem. So this very useful theorem that you can use it. It's called sandwich theorem. So let me know if it is done in the class. Okay, I was looking at the lecture notes and I think it was not done. But I didn't look at the video. So if it is done, please let me know. So let's say you have 3 functions. Okay, so you have function f, you have function g, and you have function h. Okay, be a real valued function. Okay. So I mean the function have a appropriate domain, so you can do whatever the operation that I want to do. But for now, let's assume the functions are from R to R. Okay. So it's not necessary the function is need to be from R to R. You just have to have the functions from the same domain, so it will be useful. Okay. Real world function such that what happens is f of x is less than or equal to g of x is less than or equal to h of x. Okay, so I have a function like that where what I know is at least in last 2 weeks it was not done. Yeah. Okay, so that's good, but it's a very kind of useful theorem, so one can kind of use it. So let's use it here. So I have 3 function f, g, and h such that what happens is this g of x is kind of, see, if you look at the sandwich, it looks like there is a bun and there is something inside, depending on whatever your choice is, and there is another one, right? So you can see it as f, see it as g, and see it as h, and then this g is sandwiched between the f and h. Okay, so the same kind of thing is going on here. So that's why it's called the sandwich theorem. So now you have a function like this. Then what you know is the limit of so the limit also has to have the same property. Okay. So f of x is less than or equal to limit x tends to a, g of x limit x tends to a, h of x. Okay. So this theorem is called the sandwich theorem, and it's very useful. So whenever you do with the limit, then you can also talk about the continuity, right? So if you have a continuous function, the limit can be, well, I mean, there's not much to talk about the limit, but yeah. Yeah, so this is the theorem, and it will be useful because sometimes your g will be a function which is not very easy to work with. Okay, so for example, most of the time what happens here, if you look, say I know this in this limit, right? So I'm going to use this limit with some approximate some idea like this. So I'm taking the limit, I have a limit like this. Now I will split the limit, right? So if you are using the algebra of limit with whatever the limit and we do some manipulation, and then we'll try to solve this, right? So most of the time what happens is there's no easy manipulation that you can do with this particular G. Then what happens is you can kind of use this and this, and if these two limit, let's say, has the same value, okay, suppose if this is L and this is also L, then what we know is that tells you that limit of G is also L, okay. So in some sense what happens is, instead of finding the limit here, uh, you can find the limit of these two functions, and these two functions are not very hard to find in some cases, okay. And when you can do that, you can get this limit for free. Okay, so I didn't prepare this problem. Whenever we did this, I had this idea, okay, I should tell this because this is a very interesting theorem. So maybe next class I will come up with a lot of examples to do this, and it is one of the very very useful theorem, okay. So but keep it in mind, it's very useful. So okay, so one thing I was telling is, because if you look at the sin x by x proof, this kind of idea comes. So that's why I kind of got to know, okay, I should tell this theorem. But uh, so you can try to prove this theorem if you want. Try to use the epsilon delta, and you can try to prove it. It may not be very easy to prove it, but it's very useful theorem. So at least keep that in mind. Okay. So the idea is something like this. So I have a function like this. Let's say. hmm, Here I have a f here. Uh, Okay, let me call this g. Okay, and let's say I have a h here. So I have h here, and let's say I have f below. So what it tells you is, if I'm, let's say I'm approaching at this point. Okay, maybe I'll cut it at this point. Okay, so let's say I'm approaching this point from this direction. Okay, when I'm approaching both directions, let's say you approach. When you do that, uh, all these points, this g is bounded by this f and h, right? So the limit also has to have the same property, right? So that is basically what it tells you. It's not telling you anything serious. What it tells you is, this f, if you come like this, the g is below, and here also f is below. Sorry, f is above the g, and g is below the h. It kind of comes like that. Then at the point where you have the limit also, the same property holds. So that's what it tells, and it's very useful sometimes, because whenever this, so if you have a function, let's say something like this, where you have a h here, and you have let's say, uh, okay, I have to draw it properly. So you have a function like this, let's say you have a f, and you have a h something like this, and you have a g coming like this, okay. So at this point, if you want to find the limit, you of the limit of g, you don't have to find the limit of g per se. You just have to find the limit of f and the limit of h. Okay, and then you can find it, and it will be very useful. But anyway, we will do it in the next class maybe. So right now we'll move on to next question. So the question is, if the limit f tends to a, f of x exists, okay, then does that means limit x tends to a, modulus of f of x also exists? Okay, this you probably take some time, okay. Um, and if you think it is true or false, if it is false, try to give a counter example. If it is true, you have to prove it. So it might take a while. We will do it, but uh, if you think for a little bit, then you will have some idea, okay, how these things are. So you say it's true, yeah. But the proof is, do you have the proof? So if you say it's true, yeah, you have the proof. Okay, great. But anyway, let's try to prove it. I mean, what he said is correct. Actually, it's true. Uh, but let's try to see. Okay, so this problem is not going to be algebra of limit. Okay, here we are going to use the epsilon delta. So I'm taking this problem because I mean, sometimes you may feel a little scared to use that epsilon delta definition. Here I just want to use it. It's not a serious epsilon delta computation, but we just use it. I mean, let's just do a simple one first, at least. Okay, so let's do it. So what we know is limit extends to a f of x exists, right? So that means what? That means for all epsilon greater than 0. Okay. Uh, of course, this epsilon depends on the choice of a also. It depends on the a as well as yeah, it depends on the a. So there exists delta. See, now one thing you have to observe is this delta also depends on epsilon. It's not only depend on the a, it also depends on the epsilon. Okay. So for each of this epsilon, you will have a delta. Okay. So this, if you want, you can write as delta epsilon, but to just to to emphasize that this delta depends on this epsilon. But anyway, I'll just write delta. I hope it's understand. So there is a delta greater than 0 such that so whenever x minus a is less than epsilon, so this implies basically means if this happens, then whatever I'm telling happens. Okay, that's the symbol. Sometimes people write whenever this the other happens. It's all the same, just a different way of writing it. So I'll just interchange it different. I mean, each time something else. So you have f of x minus L. So less than sorry, whenever x minus a less than delta, you have f of x minus a less than epsilon. Okay, so this is the definition of limit. So if some of you does not have the intuition about it, you can just ask me, let's say in the last 20 minutes or something. Okay, so because how the limit definition of the limit is captured by this, maybe it takes some time to understand. Okay, because it's randomly some epsilon comes, some delta comes, and somebody will tell you the epsilon is very small number. I mean, how small, right? Epsilon is a number, that's all. It doesn't mean it's small or big or anything. So it can be any number. But anyway, if you have some doubt about how this definition captures this idea of limit, then you can ask me later. I hope some of you might have the doubt. But right now, let's assume that this is understand and we'll proceed. Okay, so now what I have to see is the limit of extends to a modulus of f of x also exists, right? So that means what? So that means given epsilon, so let's say let epsilon greater than 0 be given. What I need to find is this delta. Okay, so this is what I want to find. So I need to find a delta. Let's remember that. Such that what has to happen is whenever the x minus a is less than, let's say, delta, well, this delta and this delta need not to be same, so maybe I'll change it to instead of delta I can put some symbol, let's say gamma or something, but I don't know if you're okay with that. Let me write delta of mod f. Okay, so this is a delta of f because this delta is the delta for this function and I have a different function here. Okay, so whenever this is, I have to say f of x. So mod of f of x minus mod of L. I have to say it is less than epsilon. Okay, so this is what I want to say. Now my aim is to find this delta. So I just have to say this delta exists such that this holds. Okay. So what we know is if I have f of x minus L, then this thing holds. But I'm here stuck with the modulus of f of x minus modulus of L. Okay. So here we are going to use something called reverse triangular inequality. Okay. So the reverse triangle inequality says the following: if you have two numbers, let's say x and y, okay, then modulus of x minus modulus of y is always less than or equal to modulus of x minus y. Okay, so this is basically the reverse triangle inequality. Uh, I mean, because it's called reverse triangle inequality because there is something called the triangle inequality. So I will just write that also. Of course, if you have done the real analysis, this is like a, at least the triangle inequality you would have seen because it comes in the metric space. But uh, for the calculus course, this is a really new thing. So the triangle inequality says the following: it's if you have modulus of x plus y, this is less than or equal to modulus of x plus modulus of y. Okay. So basically, the triangle inequality gives you the upper bound for this modulus of x plus y. Okay. And if you look at the reverse triangle inequality, this gives you the lower bound for this thing. So yeah, so in some sense it gives you the lower bound. That is why it is called reverse triangle inequality. Okay, so do you want me to prove this, or should I just skip the proof and assume it is true? So if you want me to prove that, I can give you a geometric proof. I mean, I say something about a triangle, right? So it has to do something about the triangle. So basically, what this says, if you want to, anyways, since I have started, probably I'll just do. Yeah, I will just give some idea also. Although this is not a calculus part, but uh, basically, this ideas of calculus, this kind of idea of calculus are useful, and you can see a geometry here. So I will just do anyway. So what this tells you, if you want to look at geometrically, it tells you the a side of a triangle. If you want to imagine like this, a side of a triangle, no, is always. I mean, not a side, a length of a side of a triangle. The length. Side of triangle is always greater than the difference of other two sides. Okay. On the two sides. Okay, so that is what this is basically telling you. Okay, so okay, how do you see that? I mean, this is some only two numbers are there, right? But I'm writing something, calling it as a reverse triangle inequality. So you see it like this. Okay, let's say you are working with a coordinate geometry where you have a 0 here. Okay, and here you have this vector a, let's say x. So your triangle you put it like this. Okay, such that one of the coordinate is 0. Okay, so just give me a minute. Yeah, this is the x vector. This is the x vector. This is y vector. So if you look at the length of this vector, that is a modulus of x, and length of this vector, this is modulus of y. So I have a two length here. Okay. So what is the this side? So this is basically this side is basically has the length uh, modulus of x minus y, right? So basically, this is all are vectors here. This is x vector, this is y vector, and this is x minus y. Okay, x vector minus y vector. Minus vector. So basically, what happens is you take a triangle and make sure that one of the vertex is in the origin. Okay, so then one of the length became x vector. Sorry, one of the side became x vector, and the length of the vector is basically mod x. Okay, and the another side became mod y, the length of the other side, and this is basically mod of x vector minus y vector, but that's basically mod of x minus y. Okay, so if you look at the length of this, the length of this vector is basically x minus y. So what it tells you is the side of this is always greater than or equal to the difference of this side and this side. So that is what it tells you. So how do you prove it? That one can prove it, but maybe just give me a minute. I can try to see if I can prove it. I mean, I'm just trying to see if I can just prove it geometrically. Otherwise, one has to use this dot product etc. to prove it, which I don't want to go into. If I have a real geometric idea, I can prove. I think I may not have it. Yeah, I think anyway. Let's just skip the proof of it. I mean, you have to use some a dot b equal to, I mean, some kind of a vector algebra to prove it. But okay, there's a comment. The sum of two sides is greater than the third. Yeah, the sum of two sides is greater than the third side, and that is basically the triangle inequality. Okay. No, sum of two sides is greater than the third side. Yeah, but basically that's a triangle inequality. Uh, okay, I think yeah, that is the triangle inequality, and this is basically not the triangle inequality. This is a reverse triangle inequality. Okay, so this is a reverse triangle inequality, and triangle inequality is a little bit different. But just give me 1 minute. Yeah. So there is another comment. I will just check. Can you prove it using triangle inequality? Yeah, of course. If you have a triangle inequality, you can prove this. You just have to do a little bit of modification and you will get it. So, I mean, yeah, you are right. Actually, we can try to use triangle inequality and prove it. But see, but I haven't prepared for this, but so I have to try to prove it. So this is the triangle inequality. Okay. So let's try to use the triangle inequality and then try to prove it. So I need to keep the y here. So I want to move the y onto the other side, but I want this one to become x. Okay. So I want to put minus x y. Okay. Yeah. So you will write like this. So this is basically. So okay. Thank you for the hint. So I got it now. You can use minus x plus y. I think this will work. Maybe not. No, I don't want to use that. Minus y plus x. I want to just get the x, right? So no, I want to get x minus y plus y. Okay, so let's take this one and we apply the triangle inequality now. Okay, so if you apply the triangle inequality, you will get mod of this is less than or equal to mod of x minus y plus mod of y, and yeah, you got it now. So this is a you can cancel out y and y, so you get mod of x less than or equal to mod of x minus y plus mod of y. Okay, and then take this to the other side. You will get mod of x minus mod of y is less than or equal to mod of x minus y. Okay, so you can get it from a triangle inequality. Basically, just put it the correct one. But what I was trying here is I'm trying to see geometrically. I mean, one can project it onto the other, and you can get it. So this proof is nice, but some way, I just want to do it geometrically. That's why I was actually trying. Uh, when prepared, I had some idea, but I didn't write it down. That's the problem. So you can write this proof, but you can actually see it with just the triangle, and it will be very obvious that it comes like that. So I was trying that, but I think either my idea is wrong, or I should have written it down. But anyway, the proof is kind of like that. You just use the triangle inequality with the appropriate thing here. So how do you come up with that? I don't know. You just have to come up with that, and then when you apply the triangle inequality, you will get like this. Okay. Okay. Since we have this reverse triangle inequality, and let's try to solve this part. So we'll add another page here. So what we have here, maybe for the time being, I will just rotate it like this so that we can use it properly. So what we know is we have this and we want this, right? So let's start with, so I want to find what is this delta here. Let's come back to the delta, but let's try to do this one. F of x minus modulus of L, if you look. Now I apply the reverse triangle inequality. This is nothing but mod of f of x minus L. Okay. And mod is nothing but just mod of f of x minus L. So what I have proved, what we have seen is this particular part which comes here. This is less than or equal to this part. Okay. So on this part is of course is less than or equal to whatever the epsilon you have, provided you have to choose a delta. But then if you observe here, the delta f you can choose as delta itself. Okay, and where the delta comes from your first limit. Okay, so you can choose the same delta. Even if you choose the same delta, it works for here, because let's say you choose the delta mod f as just the delta, and if you look at this term, by applying the reverse triangle inequality, it's less than or equal to this term, but this term is less than or equal to epsilon, provided your x minus a is less than or equal to delta. Okay, and we have chosen exactly the delta. Okay, so you have proved it. So basically you have to find a delta, and this is how you find a delta. What usually you do is here I just apply one triangle inequality and then you got it. Most of the time what happens is you cannot just apply one triangle equality and you cannot get it. So you have to apply multiple things and you have to do a lot of manipulation to get it. That's the only difference. But the idea is basically you have to find this delta. That's it. Okay, so let's move on to a different question. Yeah, but I was really disappointed. I had some nice idea there. But anyway, I will see if I can get it before the end of the class. I will tell you. Okay. So let's come here. The question is a polynomial function a continuous function? Okay. So a polynomial function is a function of the form f of x is a naught plus a1x plus a2x square plus etc. plus an x power n, where this ai's belong to real number. Okay. So this is a polynomial function. Now the
Sir,
question is it? Oh yeah.
sorry to interrupt you, sir.
Yeah,
Uh,
no. Feel free to ask. If you have a question, you just ask me.
no, sir, could you please upload this recorded video of this session in the portal? Is it possible?
Yeah, once the class is over, I will upload it.
But a week one's video we couldn't see.
It was uploaded. Okay, I will check and probably I will let you know.
Okay, sir. Thank you.
Yeah. You can just send me a mail. I can let you know so I can communicate. But I think it is uploaded. Did you check there is some tab, right? I forget which tab it is. Uh,
Yes. I
no,
couldn't
if
see.
you go to, there is week 1, week 2, week 3, and there is something called the problem solving section below that.
Okay, sir. Wait, let me check it. Like check it.
Yeah, you check and let me know. Okay, so we'll continue here. So if you look at the polynomial functions looks like this, right? So the question is it a continuous function? So let's see if the polynomial is continuous. Yeah. Yeah, and the answer is yes. So let me write here, yes. And how will you do it? You just apply the algebra of continuous function. So if you have two continuous function, what we know is if you have continuous f and g are continuous, then what you know is f plus g is continuous, f dot g is continuous, alpha f is continuous. Okay, where this and alpha belongs to real number. Okay, so then these things are continuous, right? So you apply repeatedly. A naught is a constant function, so it is continuous. So if you look an is a constant, it is continuous. Okay, so this is continuous. Let me write ai, maybe not an. Okay, and let x is a continuous function. So what happened to x square? X square is also continuous because the product is continuous. And similarly, you do it n times. Okay, so x power n is also continuous. Okay, so then what happens? So if you have a ai xi, because this xi is continuous, a is continuous, a xi is also continuous, right? Okay. So now what happens is all this AI x's are continuous. Now what you're going to do is you're just going to keep summing, right? So a naught is continuous. Okay, a naught plus a1x. This is a continuous function. Okay. Now a2 is also a2x square. This is also continuous. This is also continuous. So sum is continuous. Now the whole thing is continuous. Now you take a3 x power 3. So this is also continuous, and the whole thing is continuous. So the entire thing is continuous, and then you keep do it. Okay. So if you want to formally write it, you have to use indexation. Okay. But I'm not formally writing it. But you just have to use these things multiple times, and you can prove that polynomial function is continuous. Okay. So do you want me to prove it formally? So if you guys don't see the indexation or something, this is the first time you want to see the proof, then I can prove it. Okay, so but let me know in the comments so that I can prove it, because I don't know if it is interesting for you guys. So if it is interesting, then I can prove it. If not, we can move on to the next question. Okay, I hope everybody knows the indexation. So yeah, I will just skip the proof of it. Basically, if you want to write it formally, you have to use the indexation. Otherwise, basically what we are doing is we are just going to use these things multiple times. Okay. Okay. So what we have here is polynomial functions are continuous. Okay. So let's keep that in mind. Let's proceed to the next question. So the next question is every even degree polynomial. So basically, it's every polynomial of even degree. So even degree means it's even degree is as a real solution. So you can see the 30 course. Thank you. Yeah. So in that below the 30 course, you can have the link, so you can use it. Okay. So is every polynomial of even degree is has a real solution, and the answer on side is okay. No, it does not have a real solution. Okay. So what is the simplest polynomial one can give? So there is another answer. So it's x square plus 1. So x square plus 1. So this is the polynomial which does not have a real solution. Okay. So if you want to see, I mean, one can prove it in different ways, but see, one of the way you can prove it is, you know, okay, I will probably prove maybe multiple ways. It doesn't matter. So one is just find the discriminant b square minus 4ac. Okay. If you find the discriminant, what you will get? So this is b square is 0, 4ac is minus 4, which is less than 0, right? So if b square minus 4ac is less than 0, then there is no real root, right? Because it is a quadratic polynomial. For a quadratic polynomial, you can apply this, but of course, this is not very convincing. If you don't want to assume this, we can prove, let's say, geometrically. Okay. So you look at x square. X square is a function like this, right? So everybody have studied the parabola, etc. So this is a y equal to x square. Okay. So if you want y equal to x square plus 1, basically what you are doing is you are taking this thing and you are just translating it up. Okay. So basically, maybe I'll draw it here. So this is my parabola. So this is my parabola, let's say. And when you are adding the 1 to it, what you are basically doing is you're taking it and you're just moving it like this. Okay. Uh, maybe I'll erase this and probably will do this properly. Okay. So let's say this is my parabola. Okay. Whenever I'm adding 1 to it, basically I start with my parabola and then I'm just translating it above. Okay. Anyway, I draw it very badly, so it's not appearing anyway. So this is what I'm doing. This is a so let's say this is y equal to x square, and this is y equal to x square plus 1. Okay. Okay, so if you clearly see here, is the x square plus 1 is ever 0. So I have parabola which goes like that. It never touches the 0, right? So you don't have any real solution. Okay. But if you want to prove analytically, of course, this is not a proof. This is just idea. If you want to prove analytically, you can prove it like this. See, x square is always positive. Whatever the real x may be, x square is always positive. So x square plus 1 is always greater than or equal to 1. Okay. It never equal to 0. That's all. So you don't have a solution here. If you have an even degree polynomial, in general you will not have a solution. There are situations where you have a solution. For example, you take x square minus 1. Okay, then you have two solutions, which are basically x minus 1 and sorry, where x equal to minus 1 and plus 1. Okay. So sometimes you have a solution, sometimes you will not have a solution. But let's look at the r degree polynomial. Okay. So now the question is the same question, but now here we are asking, suppose if we have r degree polynomial, does it always have a solution? Yeah, and okay, he says it does, but if you are new to it, it will not be very easy. So let's do it. See, at least in this problem, we didn't use any calculus, right? So let's try to use some calculus here. Okay. So what we are going to do is first what we know is this polynomial is a continuous function, right? So remember that in mind. So let's say I have polynomial. I mean, it's a odd degree polynomial. Let's say it only take a third degree polynomial. Okay. I mean, one can prove in general, but let's take the third degree polynomial. You have something like x cube plus x plus x square plus x plus 1. Let's say I take this polynomial. Okay. So this is my f of x. Now I want to find a real root for this. So, I mean, it can be any polynomial, just taking it so that it will be easy to see. Okay. So, if you look at this polynomial, what you can observe is what happens when you take the limit as x tends to infinity. What happens to this polynomial? Okay. Yeah. So, if you take this polynomial and apply f as goes to infinity, so you see this is x, right? This is x cube and x square. Everything goes to infinity, right? At x goes to infinity, of course, x cube also goes to infinity, right? X square also goes to infinity, x goes to infinity, and all of this goes to infinity. So this term, this is infinity. Okay. So, I mean, I don't need it is infinity. I'm just telling it, okay, this is, I mean, this became larger, okay? So it kind of blows up. Okay? But on the other hand, if you look at the limit extends to infinity, minus infinity, f of x, now what happens? Okay. So if you look at extends to minus infinity f of x, this goes to minus infinity. Okay, because what happens here is the x cube term. See, this is the odd term, right? So what is a x cube? If you have a negative, when x is negative, what is this? Let's say you look at something like this, minus 1 cube. Okay, minus 1 cube is nothing but minus of 1 cube, right? Or let's say I take some minus 2 cube. Okay, this is nothing but minus of 2 cube. Okay, so basically this particular term, as x goes to minus infinity, goes to minus infinity. But this term need not goes to minus infinity. This will go to plus infinity, and this will goes to minus, and etc. happen. But one can prove that as a whole, this goes to minus infinity. So if you want to see it, what you can do is just take this f of x, okay, and divide by x square. So if you divide by x square, what you get is so x cube, so this will be just x plus 1 by, no, you will not get anything there. So it's 1 plus 1 by x plus 1 by x square. Okay. Now you apply a limit here. So you apply limit extends to minus infinity here. So here you can observe clearly this goes to minus infinity. And this is a 1, that does not matter because minus infinity plus 1 is just 1. And this 2 times goes to 0. So this is x square. Okay. And this 2 times goes to 0. Okay. So if you look at f of x is nothing but x square times f of x by x square. Okay. And this x square goes to minus infinity. Sorry, x square goes to infinity, and this term goes to minus infinity. Okay. So what does that tells you is you have working with infinity times minus infinity, and which is minus infinity. Yeah, I'm throwing these symbols here. Okay. Uh, I didn't want to write like this. See, one can do it without all this minus infinity times infinity equal. One can do it easily, okay. But I'm just throwing the symbols here. I mean, I hope you will not be have a problem with when I'm telling minus infinity times infinity is minus infinity. It just the minus times plus is minus, so it's kind of comes like that only. Okay, I mean it may not be very hard to do it. I mean, one can do it. Okay, so what you can do it, you have to use epsilon delta or some other estimation. Then you don't have to go to this minus infinity times infinity is minus infinity. Okay, uh, if you are fine to accept it, you can. I mean, accept it. Otherwise, you have to use some epsilon delta. Okay, or you can use some estimation. You can do it. But I'm just throwing these things here. I wouldn't like this much, but you know, let's just do this thing for right now. So whatever the purpose that I want to do, I think it's okay. Maybe not too okay, but it's okay. Okay, so if you want to see it, basically you are seeing it as f of x as f of x by x square times you are just doing another x square, and this goes to infinity, and this goes to, see, we have seen here, this is this, if you see, this goes to minus infinity. Why? Because this goes to minus infinity and this 2 goes to 0. This is a constant. Okay, so this is minus infinity plus 1 is just minus infinity. So what happens is you have a odd degree polynomial, and as x goes to infinity, the polynomial goes to infinity. As x goes to minus infinity, the polynomial goes to minus infinity. Okay, so that is all I have, and I don't have to worry much. So that means since the limit goes to minus infinity, that means there exists a point a such that f of a uh, is negative, right? Is negative if of a is strictly less than 0. and there exists a point b such that f of b is strictly greater than 0. Okay, here how do you show this here? Okay, here is where you need something like a sandwich lemma. Okay, if you want to prove it, what you prove, see here what I proved is this limits is infinity and minus infinity, but here I'm claiming there exists a point such that f of a is less than infinity, right? Less than 0, and there is a point something like that I'm proving, right? So if you want to do that, then you see here you can see the sandwich lemma that we have did it. Not exactly the entire sandwich lemma, but one part of the sandwich lemma would be very helpful. So each time you do, you want to kind of apply one part of the sandwich lemma. Okay. So let me go and apply it here. So why I'm just claiming this is true. Suppose if it is not true, suppose let's say f of x is greater than or equal to 0 for all x belongs to R. Okay, let's say if this was the case, then what happened? Then you use the sandwich lemma. Then if you use the sandwich lemma, limit as x goes to infinity. Okay, x goes to minus infinity. F of x. So this has to be greater than limit as x goes to minus infinity 0. So that means your limit has to be greater than or equal to 0, right? This is 0. But what we have is the limit is actually minus infinity. So that's a contradiction. So the contradiction arises because you're assuming that f of x is greater than or equal to 0 for all x. Okay. Well, that is not, then this is not true. That means there exists a point A such that f of A is less than or equal to 0, right? So you can similarly use the same argument, and then you can prove that there exists a point B such that f of B is greater than or equal to 0. Okay. So now you got 2 points. One is greater than or equal to 0 and one is less than or equal to 0. So now you have a function. I don't know what the function is, but there is 2 points. Let's say there's a point A and I mean there's a point B here. See here also I can without loss of generality assume that A is less than or equal to B. In general, there is no need that this A is less than or equal to B. But if you want, what you can observe, I mean, you have to modify this argument little bit and to make sure that you can get A is less than or equal to B. Okay. So basically, let's say you first proved this. So you have point B such that f of B is greater than or equal to 0. So from here onwards, I mean not necessarily here onwards, this point, your f of B is greater than or equal to 0. Okay. Now if I want to get a, this A can be either here, it can be here also, right? So I have to tweak it a little bit. So instead of telling for all x greater than or equal to R, I'll just do for all x less than or equal to B. So for not, instead of saying for all x belongs to R, I'll just say for all x less than B. Okay, you just do this. Now why it makes sense is because you are doing the limit as x goes to minus infinity, right? So sorry, the B is here. I'm going x goes to minus infinity. I'm going like this. So it doesn't matter if I start with here and go, or if I start with here and go, or I start with here and go. What I'm going to see is as x uh, becoming smaller and smaller and smaller, what is happening is what I care about, right? So I can start with this point B and then I can move from here onwards. Since the limit x goes to minus infinity, so I can do the same thing. So the limit does not change irrespective of whether you are starting the x when x is less than or equal to b or x is less than or equal to this point, doesn't matter. Okay, for the limit. So the same argument holds. Okay, so if this was the case, then you will get your limit is greater than or equal to 0, but then your limit is minus infinity. That is not true. But so that means you can get a point such that it is less than or equal to 0. Okay, and that point will be less. Okay, let me call strictly less than b. Okay, So that point is strictly less than b, and then you got this point a. I mean, you're just doing little bit. You're just changing it little bit. While changing it little bit, you can get what you want. Okay, there's a comment. It's no this question. Yeah. Okay. Okay. Now, now since we have it, let's try to finish it. So this f of a is somewhere here. Now it's a matter of applying the intermediate value theorem. Okay. Because you, by intermediate value theorem, you know that. So let me write by intermediate value theorem. We know. So that is point C such that C where the C belongs to this A and B such that f of C is 0. Okay, so basically we are using the intermediate value theorem. So we have the setup of intermediate theorem where the A is here. So f of A is there, f of B is there. So if there is a function that starts from A to B, at some point it crosses this 0. That's what it tells. Okay, right? We are just using the intermediate value theorem. We are just setting up the intermediate value theorem for which you want to find this point A and B such that this f of A is less than f of B. Okay, that setup you want. To do that, you are just looking at the limits, and then you proved that as x tends to infinity, it is infinity. That means at some point, uh, B, your f of A is greater than 0, right? F of B is greater than 0. And since as it goes, the function goes here, the function is going down and down. Okay, it goes to minus infinity. That means that there's a point, let's say A, at which f of A is, here. I mean, f of A can be here also. I mean, A can be here also, and f of A. Okay. Some points you will get A and B. That's all. And we just use our intermediate value theorem, we'll get the answer. Okay, so what it tells you is if you have a odd degree polynomial, it always have a real root. Okay, so see this polynomials, these are somewhat of a algebraic thing, right? People are in algebra interested in find okay whether it has a real solution, etc. But now by seeing it as a continuous function, you kind of solved it. You are not trying to manipulate it. You are not trying to find exactly what the x is, but you are telling there is a x, right? That was the interesting thing. And the another thing is it does not tells you where is the x. If you look at the proof, I mean, where is that C? I mean, I don't know, but the C is there somewhere. So it only tells you the existence of the C. It does not tell you whether the C exists or not, and it's not even telling you whether if the C exists, whether it's unique or not. Nothing is telling, but just it's telling there is a C. But even by knowing there's a C is actually very interesting, right? So if you have a R degree polynomial, you always have a real solution. Okay, let's move on to this one. This is a little bit interesting. Not very hard, but quite interesting. So here I have a matrix, okay, and I assume kind of the determinant of the matrix. Okay, so I have a matrix here where this x is kind of like a variable. I have some matrix here. So the question is, does there exist a x here such that the determinant of this matrix is 0? So see, this is yeah, and he said yes, yeah. So this is kind of like a problem. Now you're going to linear algebra, right? It's not exactly linear algebra. It's a matrix theory. Let's say you're doing, but let's see here. So let's find the determinant here. If you look at the determinant of this, let me call this as A, and if you find the determinant of A, you will see the determinant is. Let me compute here. So this is x into x square. So I take the x and then strike the row. This is x square, and then this will become 0. So plus 1. I'm expanding in the first row. Okay. So 1, I delete this. And this will be 0. And this will be minus 1, right? So this will be minus 1. Okay. So some polynomial here. Okay. I can change this. I mean, I took this matrix so that the determinant is easy to compute, but you can put any number you want. I'm just having one variable here. So you will get some polynomial like this. Okay, of course one can directly see and say, okay, 1 is the root, but what I was trying to say is you can change the numbers here. It doesn't matter. You can put 1,000 here or something. Well, 1,000. Yeah. Anyway, it does not depend on these things. I'm just putting the x here, and you can put 3x wherever you want. So you can look here x, and then this is some numbers here. Okay, it doesn't matter. So something like that you can always do it. Uh, just telling you, you will get a third degree polynomial here. So if you look, but this third degree polynomial is what? It's a odd order polynomial, right? It's a odd degree polynomial. So this is equal to x cube minus 1. So we just proved that if you have a odd degree polynomial, then you will have a real root. Okay. So real root means what? There exists x belongs to real number. There exists x belongs to real number, such that x cube minus 1 is equal to 0. Okay, I mean, well, that number is basically 1 if you want. But what I'm telling is you can change this number. Okay, I'm just choosing this matrix so it looks easy. Okay, so sometimes it is helping you to do these kind of problems, which are in general not exactly comes from calculus, right? That you can do. Okay, but another thing I want to say is if you have a determinant of a matrix where I'm putting x here, something like that. But if you just want to write a matrix like this, okay, if you have A, B, C, D, E, F, I, J, K, if you have a matrix like that, and if you write the determinant, and if you compute it, you will get some thing here, right? So you use the Lagrangian or something. Okay, maybe I'll just take the 2 cross 2 matrix. It's easy. Basically, you have to do the Lagrange expansion. So this is, let's say, AB minus BD. Okay. So you have this, right? If you treat each of this as a variable, then this function is a polynomial function. So it's not a polynomial function in one variable. So it's not the calculus that we are doing right now will not help us doing anything with this. But it's a polynomial in 4 variables. Okay. In 4 variables. And of course these functions are continuous. Okay, but the thing is it's not involved in our course, but that's why instead of 4 variables I'm just choosing 1 variable. Okay, there is generally one can say that determinants are polynomials, and these are continuous functions, etc. So there is something interesting about this determinants. It became, it is a polynomial. So, and the polynomials are continuous, they are differentiable, so you can do some calculus with that. Okay, we will do this problem. I think this is my last problem, but before that I will just add one more thing, which I don't know how many of you have seen it. So what the intermediate value theorem says, if you look at intermediate value theorem. So I mean, there is some hypothesis. With that hypothesis, what it says is if you have a continuous function, then it satisfied intermediate value property. Okay, so what is intermediate value property? It is basically telling if so A is less than B, then no, not A is less than B. If f of A is less than f of B, of course, if okay, let me start with A is less than B. Okay, so if f is a function defined on, let's say, a comma b to R, such that f of A is less than f of B, then there exists so let me write something like this. Okay, f of A is less than C less than f of B. Okay, then there exists alpha belongs to A comma B, such that f of alpha is equal to C. Okay, so this is what the intermediate value property. So if you look, this is exactly what the intermediate value theorem. So whatever the intermediate value theorem says, we just take it, and this property is called intermediate value property. The reason I'm saying this, yeah, the reason I'm specifying is there is a little bit of theory here. At some point, whenever the people thinks of a continuous function, when you have a intuitively think of continuous function, uh, you see it as something like a function. You can draw without taking your pencil, something like that. One may think, right? And that is actually called the intermediate value property, and that is basically what this property tells you. Okay, but this continuity, of course, implies the intermediate value property, but is the converse true? So that is the question. So if I have a intermediate value property, does that implies it is continuous? Well, the answer is it is not. Okay, so this is not true. We will give you the. I will give you an example. But before that, I will just tell you a little bit about intermediate value property. Okay, so we have a continuous function. Well, that gives intermediate value property. Okay, so we haven't thought the derivative yet, but I just since we are doing the intermediate value property, I will just say things, and when you do the derivative, you can come back and think about it. Okay, so the idea is if you have a function f, which is a differentiable function. Even if you don't know what is a differential function, don't worry about it. Next class you will study. Okay. So once you study, you can come back and kind of think, okay, this guy said something. Let me just look. Okay. If you have a differentiable function, then if you look at what you know is a differential function implies continuity. Okay. This you will prove it. Okay. But the continuous does not implies differentiable. So this differentiable is much stronger than continuity. Okay. But if you look at f prime need not to be continuous in general. Okay, it need not to be continuous. If it is need not to be continuous, that means it is need not to be differentiable also. Okay, it depends on the function. It is f prime. F prime is basically the derivative of f. Okay, which people sometimes write as df by dx. It need not to be differentiable. It need not to be continuous. But the interesting part is f prime has the intermediate value property. Okay. So if you look here, you have the intermediate value property. So continuous implies intermediate value property, and f prime has the intermediate value property. So if you see it here, so differentiability implies continuity, and it implies intermediate value property. Okay. So if you want to see, you can see it something like this. You have intermediate value property functions, and then inside that you have continuous functions, and inside that you have differentiable functions. Okay, and the derivative here. Uh, it does not false here. So if you take a derivative of a function here, it does not belongs to the same circle here. Let's say it's a Venn diagram or something. It does not belongs to the same set. It does not even belongs to this set also, but it belongs to this bigger set. Okay, that's what I was telling. But I'm not defining what is the derivative, etc. This will be in the next week. But since we are discussing it, I'm just throwing it here. Okay, so the question, let's come back to the question whether the continuous function implies intermediate value property, and the answer is no. I told you. So what is the example? So I have to give you example, right? So let's go back to some functions that which we have already done it. So let me take it here. I told you that I will come back to here, right? So let's look at this function. Okay, does this has intermediate value property? So if you look, it does not have intermediate value property, right? So 1 0. I don't know where you said 1.0 or 1 comma 0. I don't know. I think I missed the comment, but yeah. So if you look, this does not have intermediate value property, right? This is a discontinuous function, but Okay, yeah, supremum infimum problem. Okay, we'll come back to the supremum infimum problem, but let's prove this intermediate value property. Okay, so if you look at this function, it does not have intermediate value property. So it's a jump discontinuity because here I have -1, here I have 1. But then if you look at, let's say, point like this, and there is only one point 0 here, and it maps to 0, right? It cannot have here. So this is a discontinuous function, but it does not have intermediate property. But you look at this function, okay, and this function has an intermediate value property. Why? Because you choose any a and b, doesn't matter. If you choose a and b here, then it doesn't matter, because see, if you go anywhere, start from anywhere other than 0, this function is a continuous function. Okay, so if it is a continuous function, it has intermediate value property. So only when you have chosen one of the point as a, so let's say 0, a equal to 0, then you choose some point b. That's where you have this, whether you want to check whether it is an intermediate value property or not, comes. Because otherwise, you have a continuous function, you are working with a continuous function, there's nothing to prove, because continuous functions are intermediate value by itself. Okay, let's take, you take a here. Okay, so a is 0, and you take any b here, doesn't matter. Let's say you take this b. Okay? And let's say f of b is somewhere here. Okay, and f of a is 0. Then how do you find a point such that whatever inside you want? Okay, how do you find is the following. I'm not uh, giving you the proof per se, but you see the oscillation is going seriously high here, right? So if you look near the point A, so maybe I'll draw it here. So I'm not giving the proof. One can do the proof. Proof will take. I mean, it's not very hard, but uh, I mean, I don't know if I want to give the proof. That's what I was trying to say. So you start with the 0, and you. So this is 0 is my A, okay, and let it be any B, and it goes something along like this. But here, if you see, there are oscillation like this, right? So let's say my B is okay. I'll probably draw it properly. So this is my B, and let's say B start like this, and you can see there are huge oscillations here going like this. So whatever the B may be, and your A, it is 0. F of A is actually 0 out of the B's. So if you look here, what I can do is I can always take one point here. Okay, so I take another point here, which is also 0. Okay, because before the B, when you go like this, since it is oscillating too much, I can always take a point here which is 0. Okay, now what you do is you apply intermediate, and if you look from in this interval, it is a continuous function, right? It is only discontinuous at this point, and every point other than this, it's a continuous function. So you look at the function from here to here. Again, it's a continuous function, and it has the intermediate value property, right? So, and this 0, f of a is 0, same as this f of a is equal to 0. So basically, you have intermediate value property here. So basically, whatever the f of c may be, let's say you want to whatever the c may be, let's say call it c, then I can always get alpha here between this range, such that f of alpha is this c. Okay. So if I get alpha inside this range, that means I'm getting alpha in the bigger range, right? So it has an intermediate value property. This function, it has intermediate value property. Okay, but it is not a continuous function. So that was the interesting point about it. I'm not proving this. One can prove it if you want. Uh, Maybe if you're interested, I can just give you a hint. How do you see, the problem is to find this point where it is 0, right? So let's say I take B here. Okay, let's say this is my B here. I basically want to find a 0 here other than this point, right? So you want to look at something like a sine. Uh, so this is 1 by x, right? So you want to look at x equal to 1 by n pi, something along this x you have to look. Okay, n pi or 2 n pi. Okay, because at sine of 2 n pi is 0. Okay, so that is what you are going to use. So if you look at the sign of 1 by 2n pi, which is nothing but sine of 2n pi, and that will be 0. So you have to find 2n pi. See, and you know it is 1 by 2n pi, and as n goes to infinity, this goes to 0. This whole term goes to 0. So 1 by 2n pi's are here. These are exactly these points. Okay, so using that you have to find using the limit, and then you have to do some estimation, and you have to find. Okay, I'm not doing it, I'm just telling you the idea, but the idea is basically what kind of a point you find where the f of a is 0 is basically you look for this point of this form 1 by 2 pi n. Okay, 2 n pi, yeah. Okay, you find those points, and then you can probably keep it as a homework. Okay, it's not impossible. One has to do a little bit of estimation, so you can keep it as a homework. But it may be little hard. Uh, if you never have done it before, it may be little hard. Okay, let's look at this problem. Okay, and now I got what you are actually telling here. So, okay, so this is the last problem for this session. So I have a set here. So let's find the supremum and infimum of this set. So the supremum is basically least upper bound, right? So here, if you look at 1 here, and the next term will be 1 by 2, 1 by 3, and it is kind of going like that, right? 1 by 4, etc. Okay, it's going like this. So the upper bound or the least upper bound is basically 1. Okay, so the supremum is 1, and the infimum, if you look, because if you look at the limit of extends to infinity 1 by x, if you look at the limit, that limit is basically not x, 1 by x. Yeah, the limit is basically 0. Okay, so these terms are going to 0. So if you draw a number line, you start with 1, and then you go 1 by 2, and then etc. You go, and you will go as close as 0 you want. Okay, so the limit is the 0. So okay, so let's do this. See, the thing is, I mean, I hope you understand uh, intuitively what the epsilon, say what the limit says, right? So basically, what happens is you have a function here. Let's say I just try a function like this, and you have a point A. Okay, and then what you are trying is you want trying to see, okay, if I approaches to A, then what happens to my function? Okay, that is what you are trying to see. That's the basic idea behind the limit, right? Because sometimes what happens is your function is of the form 0 by 0 at this point. So at this point you don't know what is going on. So you are trying to go like this, and then you're trying to find, okay, what happens at this point. So that's what you're interested in, right? Now the same thing, I want to kind of make it rigorous. So that was the idea. So you have intuition what limit extends to a f of x is equal to L. Okay. So let's say this point is L. Okay. Okay. I mean, this point is, let's say, L. And this point is A. Now you're claiming the limit, and then you're seeing here as your function goes to A here, your f of x kind of goes to this point L. So this here, if you want to see. So as A is going here, f of A is moving towards L. So that is what you see. Now the question is, okay, then how do I prove it? Okay, so let's try to rigorously, I mean, let's try to see it. Okay, so here what I'm telling is, as I goes f of x closer and closer to A, this f of x here goes closer and closer to L, right? That's what I'm telling. That's the kind of the intuition behind the uh, limit. So now one asks a question, okay? So if you're telling me as f of A goes closer and closer to A, and you are telling me that f of x also going close and close to L. So the question is, okay, how close it goes to L, right? So can it go arbitrary close, or can it go only some close? Okay, so you are asking me how close, and I am telling you however close you want. Okay, so whatever the epsilon, so epsilon is basically this distance. Okay, so the distance between these two, this is epsilon. So whatever the distance here may be, you tell me whatever the however close you want. Okay, so that's what I'm telling. For all epsilon greater than 0, whatever this distance you want, so I can. So how do I make it uh, this f of x go closer to L? I'll make f of x go closer to L by making the x going closer and closer to A. That's what I'm telling you, right? So whatever the however the closeness you want here, I can change this x, making it close to A, such that something I'm going to tell you. I mean, so whatever the closeness you want, I can make a this x going closer to A. That closeness I'm just calling as delta. Okay. So whatever you want, I'm going to choose a distance here. So there exists a delta greater than 0, such that if you look at this neighborhood, the image of this neighborhood is contained in here. That's what you are telling, right? So that, so if you look at the ball of A, comma delta, so that's basically this neighborhood, or A minus delta. Okay, if you look at this neighborhood, the f of this neighborhood uh, is contained in L is contained in L minus epsilon, comma L plus epsilon. Okay, so that is what I am telling. Uh, you want it closer to L, and you are telling me however the closer you want, whatever the close, then you are telling me, okay, I want it epsilon close. What I'm doing is, okay, I'm just, then I will make it a delta close here, such that this neighborhood, if you take the image of the neighborhood, it lands within the epsilon neighborhood. Okay, so that is basically the definition of the limit. So what it tells you is whatever the closeness you gave me, see, I'm telling you, I can make this f as close as L I want. How will I make it? I will make it as this x approach to A, right? So that's what I'm telling. However close you want, I can make this x closer to A in a way. So there exists delta. This delta tells you this closeness of this x here, such that whenever you apply the function will be close to L. Okay, and if you just rewrite these things, you will get uh, the definition. So here you have f of this is less than this, right? So instead of the entire thing belongs to here, what you write is every x belongs to this is contained here, right? So I'm telling the f of the entire set is here. That is same as telling f of every x belongs to the is here. So that means f of uh, so so this one I'm just rewriting it. So for all epsilon greater than 0, there exists a delta greater than 0, such that if x belongs to A minus delta, comma A plus delta, I'm telling, so whenever x is belongs to this region, my image of this has to belongs to this, right? So whenever it belongs to this, f of x belongs to L minus epsilon, comma L plus epsilon. Okay. And if you rewrite it again, uh, you will get x minus a less than delta implies f of x minus L less than epsilon. Okay, and just change the words here. You will get whenever x minus a less than delta f of x minus L less than epsilon. Okay, so this is the idea. The intuition is what you are telling is I'm telling uh, as the x goes closer to a, f of x goes closer to L. Okay, so that was the intuition. So okay, one ask, okay, you are making it closer to a, and you are telling me that f of x is going closer to L. Then you ask me, okay, how close you can make it, and I'm telling you whatever the close you want. Okay, whatever the closeness you give, by making this delta, by making this x closer to a, I can make the image of this f of x going closer to L. Okay, so that's the idea. So and then rewriting the idea, you will get whatever you want. So it's the same thing. What this line and this line is the same thing. It's just the rewrite of that. So do you got some idea now? Yeah. So if you have a, still you're having some problem, you can just ask me. I can tell you, because whatever I say, if you are not happy about that, well, you can still ask me. Okay. Otherwise, you think for a while. It might take a while. Whatever I tell you, it might take a while, and then you think for a while, and then you can ask. Maybe later next class also you can ask. But see it like this way. Okay. Uh, a ball which is close enough to A, or a neighborhood close enough to A, the image of this is close enough to this. This is much interesting way to do it. I mean, of course, I just have to say, uh, even though it is this one, I'm not taking the A here. Okay, so this is this set, difference the A. Okay, I don't care about what happens at A. So in this case also, it is 0 less than like this. Okay, so I have to change it here.